Thousands of years ago, the night sky was the only laboratory for the human eye. No satellites, no city lights, and no glass lenses. Within this darkness, observers in India plotted the paths of 27 distinct lunar constellations, known as nakshatras. They used purely mathematical observation to track planetary orbits with high precision. By calculating the intersection of these orbits, these early scientists could predict the exact timing of solar and lunar eclipses long before the events occurred. These records prioritized geometric proof over mythological storytelling, establishing a tradition of unassisted scientific inquiry. Centuries before the technology existed to leave the ground, the internal logic of the cosmos had already been mapped from the Earth. By the 5th century, much of the world operated under the assumption that the Earth remained completely still. Aryabhata challenged this consensus. He proposed a model where the Earth rotates on its own axes, explaining the apparent movement of the stars as a result of our own planet's motion. Later, Varahamihira expanded this work, identifying correlations between these planetary cycles and terrestrial phenomena like weather patterns and seismic activity. Their collective work organized the sky into a predictable, mathematically bound system. As mathematical theories matured, they were translated into physical architecture designed to verify them. The Jantar-Mantar observatories use these massive stone curves to track celestial bodies. By measuring the length and angle of shadows, these instruments could determine the time and the position of planets without a single moving part. This engineering turned abstract geometry into tangible measuring tools, bridging the gap between theory and hardware. Following centuries of observation, the objective shifted toward physical exploration. Vikram Sarabhai argued that a developing nation could not afford to ignore space technology. He believed that satellite data was essential for India's modernization, even with limited financial resources. APJ Abdul Kalam became the lead engineer for this vision. He rose from a humble background to direct the technical efforts that would finally move India's scientific focus from the ground to the atmosphere. During the early stages of the program, rocket components were transported to the launch site on the back of bicycles. This minimal infrastructure eventually produced the SLV-3, India's first satellite launch vehicle. The success of early launches demonstrated that intellectual resolve could overcome a lack of industrial wealth. That same spirit now powers modern heavy-lift rockets, positioning ISRO as a primary player in global space exploration. In 2008, the Chandrayaan mission successfully identified water molecules on the lunar surface, changing the global scientific understanding of the Moon. With Mangalyaan, India became the first nation to successfully reach Mars orbit on its initial attempt, a milestone in cost-effective orbital mechanics. This momentum continued with Chandrayaan-3, which completed a historic landing on the unexplored lunar South Pole. These results represent the long-term compounding of a mathematical tradition that began with ancient observations. This evolution, moving from reading the sky to establishing a physical presence within it, took thousands of years to complete. It reflects the philosophy Kalam often shared, that true scientific ambition is a force that refuses to remain dormant until the work is finished. India's exploratory identity now extends well beyond its terrestrial borders. A civilization that once studied the stars from the darkness of the Earth is now actively participating in the exploration of the cosmos.